Namaste mere pyare bachcho. Welcome back. With your exams just around the corner, I know things are getting a bit tense. So, let's pick a chapter that is super simple and a real score booster, the kinetic theory of gases. We're going to make this so easy, you'll remember it forever. Chalo, let's get started.
So think about this for a second. Your mom is making delicious hot samosas in the kitchen. We're always told that gas molecules are flying around at crazy speeds, hundreds of meters per second. So why doesn't that amazing smell hit you instantly? It's a great question, and by the end of our little chat today, you'll know the secret.
Okay, so before we zoom in to the tiny, invisible world of molecules, let's start with the big picture. The stuff we can actually see and measure. What are the simple rules that all gases seem to follow? And here it is, the superstar of the chapter, PV equals nRT. I'm sure you've seen this equation so many times, and for a very good reason. It's the golden rule that connects pressure, volume, and temperature all in one beautiful, simple package. This is our starting point for everything. And you know what's so cool about this equation? It's like a master key. It unlocks all the other gas laws that you studied. Boyle's law, Charles' law, all of them. They all just pop right out of this one powerful formula. It's the boss.
So, that was the big outside view. Now, let's become detectives. Jetto, let's zoom in, way in, and see what's really happening with the tiny molecules inside the gas. What are they actually doing in there?
The whole idea of kinetic theory is actually quite simple. Just imagine a box filled with billions and billions of tiny, super-fast particles. They're all just randomly moving, bumping into each other, bouncing off the walls. It's like a chaotic dance party in there.
So, this brings up a question. Where does gas pressure even come from? Well, it's all because of this chaotic dance. Picture just one of these tiny molecules. It's on a mission, flying straight towards the wall of the container. And bang! It hits the wall and bounces right back.
Now think about it. Every single time a molecule hits the wall and bounces back, its direction changes, right? And that means its momentum changes. And remember what our good friend Newton told us? A change in momentum creates a force. So every little collision gives the wall a tiny, tiny push.
Okay, but that's just one molecule. Now imagine not one, but billions upon billions of molecules doing this, hitting the walls every single second. All those tiny, tiny pushes add up to create the constant pressure we can actually measure. And this leads us to this super important formula. Please note this one down, it's an exam hotspot.
All right, so we've connected pressure to molecules bumping into walls. That's cool. But what about temperature? What is temperature at this tiny molecular level? This, my dear students, is where the real aha moment happens. We're about to connect the big world we see with the tiny world we can't.
So, on one side, we have temperature, right? The thing we measure with a thermometer. On the other side, we have the average kinetic energy of the molecules. That's just a fancy way of saying how much energy they have because of their movement, how much Josh they have. And guess what? These two things are not just related, they're basically the same thing. This is the golden rule, bachcho. A higher temperature doesn't mean anything magical. It simply means that on average, the molecules inside are moving faster and have more kinetic energy. That's it. Temperature is just a report card for the average energy of the molecules. Simple, isn't it?
Okay, quiz time. Let's see if you're with me. Imagine we have two gases in two boxes, argon and chlorine. Argon is much lighter than chlorine. If both gases are at the exact same temperature, which molecules do you think are moving faster? The heavy chlorine ones or the light argon ones? Think for a second.
And the answer is the lighter ones. The argon molecules are moving faster. Why? Well, if the temperature is the same, their average kinetic energy has to be the same. And since kinetic energy depends on both mass and speed, for the energy to be equal, the little guy with less mass has to move much faster to keep up. Makes sense, right?
Okay, let's go just one level deeper. We know these molecules have energy from moving around, but how exactly is this energy stored? Can they only move from point A to point B, or can they do other things like spin or vibrate? This brings us to a cool idea called degrees of freedom. Let's start with a simple one, a monatomic gas like helium. It's just a single atom, like a tiny little ball. It can move left and right, that's one way. It can move forward and backward, that's two. And it can move up and down, that's three. 3 independent ways to move and store energy. So we say it has 3 degrees of freedom. Easy.
Now what about something like oxygen, which has two atoms joined together? Think of it like a little dumbbell. It can still move left-right, forward-backward, and up-down, so that's 3. But it can also rotate. It can tumble end over end, and it can spin like a top. That gives it 2 extra ways to store energy. So 3 plus 2 gives it a total of 5 degrees of freedom.
Now, why does all this matter? Because it helps us understand why different gases need different amounts of heat to raise their temperature. This table here is your best friend for solving numerical problems in the exam. Please take a good look at it and try to remember these values. It's a real shortcut.
All right, time for the final lap. Let's do a lightning-fast revision, a quick exam booster round to make sure all the most important points are fresh in your mind. Ready? Let's go.
Here they are, the top 5, the absolute must-know formulas for this chapter. The ideal gas law, the pressure formula for molecular speeds, the beautiful link between energy and temperature, the formula for root mean square speed, and finally, the mean free path. If you know these, you are in great shape. Quick, take a screenshot.
And now, for the grand finale, let's go back to our very first question. My brilliant students, if these little molecules are zipping around at 500 meters per second, that's faster than a passenger jet. Then why on earth does it take so long for the smell of those samosas to get from the kitchen to you?
And the secret is this idea called the mean free path. See, that little smell molecule doesn't get a clear, straight highway to your nose. No way. It travels a tiny distance and then bam, it collides with an air molecule. It changes direction, travels a bit more, bam, another collision. It's a zigzag journey.
So even though the molecule itself is moving incredibly fast, its overall journey is very slow and random because it keeps getting knocked around by billions of other molecules that are in its way. It's like trying to run through a super crowded market. And that, my friends, is the secret. Now you know. You're all set. Go and do your absolute best in your exams. You are going to be fantastic.